All right, welcome and hello. My name is Morten Bormann Nielsen. I'm from the Danish Technological Institute, and today in this webinar I will be telling you about a method and a tool that's easy to use that will help you develop better products or optimize your processes in the company where you work. Let's get into the material. So what I'll be talking about today is a tool and a method that delivers good results in a wide range of industries, irrespective of what you work with. It's a tool that can be used to accelerate your R&D projects, it can be used to optimize your production, and it can save you a lot of materials by recipe optimization or tweaking the ingredients that you use for your products. These companies here are examples of what you can get out of introducing the tool that I'll be talking about today, and that tool is called Brownie Bee. The tool and the method are, in combination, a solution to a relatively simple problem: finding optimal settings for a process based on a set of predetermined quality requirements. And that's a problem that's very easy to state and hard to solve in practice, as I'm sure you know if this webinar has relevance for you. I'll be talking about one effective way of solving this problem, which is to use Bayesian optimization with the tool Brownie Bee. That's the topic of today. Now, finding an optimal process in a real-world situation is difficult, and it requires us to carry out experiments. If we could just sit down and think our way to a set of process settings that would give an optimal product, we would do that. But in the real world, it's not so obvious how the things that we can control in our company's processes, things like temperature, pressure, or how quickly we add stuff to our product, how that actually affects quality, however we choose to measure that. We know there is some things that connect the factors and the quality, but we don't know exactly how strong each of these things affect our output. And to find out, we have to test and do experiments. Now, what is an experiment actually? And why should we bother designing it? How can we avoid becoming the object of the quote that I've shown here on the screen? Well, how I like to think about experiments is that we do experiments because we need measurement systems for producing data. And this data is something we use to build models of nature, including our processes. And then what we want to do is use these models to as a kind of map to find our way to the goal that we have as fast as possible. And there are many ways we could go about building this map. The most commonly used across many industry, most of industry today, is still varying things one at a time, because that's easy to understand and it's easy to sort of grasp what is happening when you just vary things one at a time. So let's imagine that we have some process whose quality we measure along the vertical scale here, and we imagine that this process might depend on temperature and time. So if we vary things one at a time, we might pick some time and set our process to that, and then we generate data at 5 different temperatures. And maybe that data looks like this. So we fix our process to this temperature, here where we have the best results, and then we will do a time series. Gather new data and then see that the best time was maybe this one, and then we can sort of keep doing this until we run out of time or budget. But in general, for complicated products and processes in the real world, this approach is almost guaranteed to not find the best solution. And our outcome really depends on the particular time we chose to keep fixed first and which particular factor we chose to experiment with first. So it's not a very robust method for finding a good solution in a given experimental system. And one of the ways you could choose instead to go about solving this problem is to use design of experiments, or DOE, which is a statistical method that is quite useful and well demonstrated and has existed for many years, more years than I have been alive. And what you do in design of experiments is that you start out by thinking about this playing field, like what is actually my factor ranges that I could operate within. And then we pick a set of experiments that we
distribute across our space in a clever way that allows us to draw the map. So here we would go out, collect the data, and use these data points to draw a map that predicts that the solution is here. Note that the amount of data, the number of data points here in the DOE case was 9, and here in the one factor at a time case was 9. But these data points are much more useful. They contain a lot more information in their combination than this data set did over here. Now, that's all well and good, but the issue, or one of the challenges of using DOE in an industrial context, is that the number of experiments that you need to run before you can draw the map becomes really big the more factors you have in your system. And typically for optimizing or processes or products, you would not really want to do a DOE for more than, say, 4 or 5 factors at a time. So 4 or 5 things we change. Otherwise, the number of experiments becomes big very quickly. Another disadvantage of DOE is that you have to choose all your experiments up front and then go out and complete all of them before you can draw the map and make conclusions and see what you've learned. And this is not something that is very natural for us humans. We prefer looking at the results as they come in and learn in a more iterative fashion. And this is where Bayesian optimization comes in. So in Bayesian optimization, we do the same initial steps as with DOE. We have to think about what playing field we are on. But instead of choosing very many experiments up front, we just choose a small number at a different set of settings for our process and go out and collect data here in these locations. And then we draw a map that we know initially is wrong, but it's still useful, because we can use some complicated math that we won't go into to figure out where is the next set of settings that are most likely to give me an improvement. And that's what I've tried to illustrate here down at the bottom of this figure here. So the more yellow we are, you could say the more useful, or the more we will learn by doing an experiment in that location. So right now, the math is pushing us to conduct an experiment in the corner here. So we collect that data point, draw the map again, do a new round of asking for a new suggestion. We get told to go down to this point where we could see an even bigger increase in quality, get a data point there, didn't improve the quality, and then get a new suggestion. We're asked to go here, and then at this stage, the map doesn't really change much, or the solutions that are suggested to us are not really changing anymore. And I think this took 6 or 7 attempts in this case. But the advantage of this method here on the right is that it scales much better to when we have many factors. Visually the difference is not very big when we just have 2, but this is just so you and I can understand what I'm talking about right now. So Bayesian optimization doesn't scale as aggressively in terms of the number of experiments we need to run compared to classic DOE. So the more towards the right you can go in your strategy for choosing your next experiment, the more information you get per experiment, the more effective you are in finding the optimum. And that comes at a cost of ease of understanding. It's much more easy to understand the bad method, one factor at a time, and much more complicated to understand the math that is happening in the Bayesian optimization. But luckily for you, you don't have to in order to make use of it. So in your context, you're probably one of several developers with technical education working in a company. And you and most of your colleagues might be at the point where you have been taught in your scientific education to vary things one at a time. And because you and your colleagues have done this for a very long time, you're probably quite confident that this is a good idea. Now, that means that you live here at the top of Mount one factor at a time. And what typically happens when someone like me comes out into a company and tries to push a better way of working into a development team, either design of experiments or Bayesian optimization, we run into challenges. With classical DOE, people frequently get a little bit scared that you get this long list of experiments that you might be asked to run. You might not know what the variation is in your quality metrics, so it's difficult to use classic DOE and figure out how many experiments we need to run. And you might also have the problem that most of your quality metrics are visual or taste-based or smell-based, and you don't measure quality, you just judge quality. And if you are in a production-focused company, you might also run into the protest from your colleagues or management that they don't care about models for the process. They just want a solution. They want a recipe that works. They want a product you can sell. We want a process that is optimal. We don't care about understanding. We care about results. That means that when you try to learn a little bit more about how you can design your experiments well, you have to cross this valley of despair where all of these issues with working in a different way come up. And it would be nice if something existed that allowed you to keep doing a relatively iterative experimentation, which habit-wise is not very different from running factors one at a time, and something that didn't need you to understand all the complicated math that we can use to choose experiments, and wrapped in a simple user interface that anyone can use. That's what we hope to give you with the software Brownie Bee. So I should stress before I show you sort of how it works and the tool itself that it's in the whole, on the whole for your company, what really drives the efficiency of working in a data-driven manner is the method. And the method is what I've illustrated here. So it starts with having a clear goal for the thing we want to improve. Then we have to consider how we will measure quality and how we will do so reliably. We have to choose what factors to change and include in our study. So which levers are we going to pull and which are we not going to touch? And then with Brownie Bee, we will get into the loop of choosing an experiment, which we go and carry out. And then we update our model, our map, with the information we gain from the experiment and use that to choose a next, even better experiment, hopefully. And we stay in that cycle until we reach our goal. And hopefully Brownie Bee will make it easy for you to sort of get into using this method, because it is, on the whole, the method that drives the efficiency. So let's take a little bit of a closer look into how does it actually work. Not with math, but with a sort of a visual explanation. And first, by way of example. So we developed Brownie Bee in a collaboration with the very large company Novo Nordisk. And a good example that they produced is how to figure out how to bake the best brownie. Now, if you don't know a lot about baking, you might be able to sort of guess at the ingredients that we might want to put in a brownie. And you might have an idea that we will probably also need to bake this cake, right? But if we don't know a lot, then we might not be sure whether we even need vanilla sugar or not, and we don't know sort of the upper limit of how much we might want to add. So therefore, for now, we're going to set the space that we're going to potentially explore very widely. And the reason we do this is that if we set it widely, then hopefully there is a solution somewhere in there. And if the math is really efficient, then it'll still be able to find that solution, even though it's hiding in a very large space. Any algorithm can find an optimum if we just restrict the space to being very near where the solution is. But when we develop new products or new processes, we don't know where the optimum is. So we can't just set a narrow range for all our factors, right? So in this case, the space is so extreme that it is an option to not make a cake and turn on the oven, right? So if our algorithms can find a solution here, then they can find a solution in most real spaces, right? So the guy who ran this experiment, Rolf is his name, the way he went about starting is that he chose 3 different recipes within this space, produced the associated brownies from those recipes, brought them to work, and asked his his colleagues in his team to score these brownies on a taste of 1 to 10 for taste, looks, and texture, or mouthfeel, if you will, right? And the quality is just then the sum of these three numbers. And here's the results from these first three, essentially random recipes. They did not result in good brownies, and this shouldn't surprise us, right? So, and especially the first one here has a score of 3, which is the worst possible brownie score you could get in this system. And that is basically because this looks like a piece of charcoal, right? But there's a really important point in these 3 data points, and that is that they're not equally bad. There is some information here about something that turns brownies slightly better or worse. And since the recipes are not identical, they contain some information about how we might want to change the recipe in order to get an even better one. So we do that using the math that lives in Brownie Bee and get this result, which has been described to me as something that looks like brownie until you put it in your mouth. And then Rolf sort of iterated on this more and more until here, after 14 brownies, he got a recipe that produced a quality of 26 out of 30. And then Rolf continued for another few runs up to maybe 20, and I don't know if he either ran out of ingredients or whether his colleagues sort of decided to say to him, this is maybe too much, brownie, please stop. But I can also share this with you. This was then the recipe he arrived at, the best one that produced the 26 out of 30 brownie. I've tried making this one as well. It's a pretty good brownie, actually. And so sort of put into perspective how difficult this problem is, I want to illustrate how difficult it would be to solve with classical design of experiments. So if you're used to using classical DOE, you would maybe consider sort of trimming down the problem by running a screening design first to figure out, are there any of our factors that don't really affect quality very much? Maybe most people can't really taste whether we add vanilla sugar or not, for instance. But to run a screening design, you would need to do at least 16 to 32 experiments, depending on your level of noise. And then after that, might be able to remove maybe 2 or 3 factors. And then you would still need to run an optimization design, so draw the full map with 6 ingredients and the 2 process factors, so temperature and time in the oven. And that would require at least another 55 experiments. And that means you would have to bake 65 or to 80 brownies before we could even begin to say whether there is a good recipe in here somewhere. And this is one reason, I think, that DOE is underused in many industries that have complicated processes where the number of factors is similar to the brownie example, where you have at least 10 things that affect your quality. Right. But let's look into how do we actually get this next recipe, and how come it can actually make use of this bad data to pick a better solution for us. So I will show you this in a graphical way. And for this example, we just have one factor here along the horizontal axis. And we measure quality along the vertical axis on a scale of 0 to 5. And you can think of this just as a star rating, basically. So we have these 4 initial data points of, again, varied quality. And now what we do is essentially what I'm sure you can't help but do now, is that we will ask for a relatively smooth trend that describes these data points. And what I mean by smooth is showed here by the green line on the top, something that varies in a relatively continuous manner. It can vary very steeply, but still in a continuous manner. Because as a chemist, I don't know any real process where the quality as a function of any relevant thing I can control, like temperature, looks like the red line here, where it just jumps up and down in a really irregular manner. So you could say we take this data set and we go down to the center of the nearest town and ask the first 1,000 people we meet to draw a relatively smooth line through this data set that describes it. And I don't know where you live, but where I live, people are not data scientists. So people will draw very different lines, and some of them will be very squiggly and others will be very smooth. And some of them will be pretty close to the data points and some of them will be slightly farther away from the data points. But if we just get enough of them, we can start to see a little bit of a picture of people draw the lines close to the data where we have them, and where we don't have any data, the lines can be very different. And instead of sort of showing this gray smear, I will just show how our data can be described by sort of the average line here, and then any quantile I would want. So maybe 95% of the lines is within the green band, right? So you can think of the green band as the uncertainty of the underlying behavior, right? Now we can use some math to take this description of our data and say, or ask the math, where are we most likely to reach our goal? Let's say our goal is to get above 4.5 in our quality. And that's what I've shown you here. So again, on the same x-axis, we get a number for how much would I like to run an experiment at each of the potential settings here. And the place where we are most likely to get an improvement is at this point, which is basically about here. Okay, so we will go out, run a new experiment here, and then we get this result, and a fairly bad one actually. Well, no problem, new trip downtown, get people to draw lines, and we have only seen sort of relatively mediocre results. But the algorithm helps us explore further, and we get this data point now. And at this point, we have actually gotten a data point that's pretty close to our goal. And that means that at this point, we might actually want to be less adventurous than before. We might want to do something that's close to this data point because we're nearly at our goal, right? So, and the math will actually support us there. So it'll ask for a point very slightly adjusted from the one we tried before. And then we get this data point. And this is a really interesting one because we did almost the same thing and we got almost the same result. And that means that we now have some information that the noise in our system actually has to be fairly small. That when we do the same thing, we will get more or less the same result. And that means that the lines that people draw, they have to be really close to the data points individually. So when we have fairly good results here, and then over here we have a really bad result, that means that there has to be a really steep trend between the bad result here and the good result here. But similarly to the other side, we also have a bad result over here. And since we assume that the process will be smooth, that means that there is a peak hiding in here somewhere in the middle. But it could also mean that there could be an even better solution out here. And since the math prioritizes not just reaching our goal, but actually also weights it by how much more than the goal can we achieve, it will want us to go away from this optimum we have found here, because it could be just a local optimum, and go out and check in the corner here whether there's an even better solution to be found there. So we do that, we get a result that's sort of right around the middle of the quality scale, and go back again, and we will continue hunting for a quality above 4.5, and then we get this data point. And now I'm just going to show you sort of the underlying system that this data is simulated from, to show you sort of this was also where the real global solution was. Now, this is sort of course, a one-dimensional problem, and for a single factor, this is actually really complicated behavior. But the way that the math chooses the next experiment is not affected by whether I have 1 or 2 or 5 or 10 factors. The math and the sort of underlying philosophy that governs our choice of the next experiment is the same. Our only assumption is that the trend through that describes our system is a fairly continuous and smooth one. It can vary quickly, but it's still going to be smooth. But enough about sort of how it works in the internal parts. let's look at the software itself and how it is to use it. So for that, I will have to stop sharing here and instead share my browser. So Brownie Bee is a browser-based tool. You can try it out at browniebee.io. There's a free trial period to start with. And it'll need you to register with your email. You don't need to sort of provide any payment details or anything to try it. And then you can log in, which I'll just do down here. And then you'll get to this interface where Brownie Bee remembers your experiments. And to get started, I will just click the Create button, which will build a new project for me here down at the bottom. And let's give it a name. So we'll call it webinar, and maybe we'll stick with the cake as an example for now. And maybe our cake will need to have flour in it, and in grams, and maybe between 200 and 400 grams. And we might need sugar, also in grams, between 100 and 200. And we might need to add eggs, and we want to add between 1 and 3 whole eggs. So I only want these to be whole numbers, so I can choose that with clicking discrete here. And then we might want to add, I don't know, cocoa in grams as well, or something like that. And if we have the kind of numbers here, and we might also have things that are not just numbers that we might want to control. So it could be a color that we add, and we might want to add a red and a green and a blue. Add these. And and you can go in, as if you made a mistake like I just did, you can go back and edit your experiment and remember to add this and then save it. Now, maybe you noticed that as I added these factors to my experiment over here, Brownie Bee has begun suggesting experiments over here on the right. And Brownie Bee will need a small number of experiments to get going. So it needs some initial data to work with. And that's what it's suggesting that you go out and do over here on the right. And it'll slowly increase the total amount that it'll ask for, depending on how many factors you put into your system. And you can choose to overwrite this over here. I would never go below what Brownie Bee recommends, but if it's easy for you to do experiments, feel free to sort of increase the initial number of points here if this is practical for you. Right, but let's trim this system down a little bit just so that it becomes easy. When we are ready to start experimenting, we can click here and transfer our suggestions to the data table down here. And once we have carried out the first experiment, we are ready to tell Brownie Bee how good the result was. And Brownie Bee expects you to provide information about quality. And it does so using a scale of 0 to 5, which you can go in here and click if you want, but you can also just type in quality, whatever it was when you did your experiment. So I will just, enter some random numbers here to just to get past the point of providing data, so that Brownie Bee can give us a suggestion for what to do next. So once we have carried out these initial experiments and scored our quality on the scale of 0 to 5, Brownie Bee is ready to analyze this data and provide suggestions for us. And the most effective way of using Brownie Bee is to ask for one experiment at a time. So up here, Brownie Bee now suggests that we go out and test the settings 200 grams of flour, 200 grams of sugar, and 1 egg, for instance. And what it shows in the plots below here is the present understanding that the model has for our system. So right now, given the very limited data we have, Brownie Bee thinks the best recipe is at about 240 grams of flour, 150 grams of sugar, and 1 egg. but it's still very uncertain, right, about the effect of eggs, especially at 2 eggs, because we only have one single data point that tested with 2 eggs. But right now, I can just show you that if you click, you get these figures in a bigger scale. And right now, it thinks that if we went out and did this experiment, we would get a quality around 4, but it's not really sure because we don't have a lot of data. But we could just transfer this data point down here and then go out and do that experiment and get some quality out of it. And as we add that, Brownie Bee will update its understanding of the system and provide us with a new suggestion here. And the graphs here will update themselves as we go along. And in the beginning, these graphs will be very wrong because we, especially in big systems, we don't have a lot of information. But let me just show you for something I've prepared, what it looks like if you have a big system and once you have progressed into having much more data. So this is a very complicated problem. So this is something to do with a PCR reaction, which is sort of the type of chemistry you use for assessing corona tests. So it's used for multiplying DNA. And here you can see that I have a lot of data, but I also have a lot of factors. I think there's like 13 things that we're varying here. And Brownie Bee has taken, again, an initial data set. I think it's like the first 15 points here are these initial data points that Brownie Bee suggested. And you can see that the quality in this initial data, as we go down here, it was really bad in the beginning. But Brownie Bee just kept exploring and then got a little bit of an improvement and kept exploring and a little bit more of an improvement. And then slowly but surely has really honed in on high quality in this very complicated system in a really low number of experiments compared to, again, what you would need with a tool like classical DOE. And here for this particular system, we can see that for instance, the denaturalization temperature is very important. So it needs to be at its maximum setting, whereas we are not really sure how bad things will get if we go to the low temperature, but we just have enough information that it will be bad. So Brownie Bee is not going to go out there and look anymore. Right. These were just a couple of examples. Let me just go back into my presentation so we can move on. I encourage you to go in and play around with it in your own time. So what I'll sort of go into next is sort of requirements and common pitfalls that we see when people begin using things like Brownie Bee or DOE in general, and how to avoid them, right? So all data-driven methods, whether you use a tool like Brownie Bee or design of experiments, require you to think a bit more upfront than if you use one factor at a time. So let's talk about that. And the first pitfall comes at the very beginning with a clearly defined goal statement. And I see lots of companies that waste resources as a consequence of getting this wrong. They do errors of the third kind, which is the error committed by giving a correct answer to the wrong question. So when a specialist hears a request for management, goes out, does a correct piece of work, and arrives at a technically correct conclusion, but it wasn't what management wanted an answer to. They thought they were asking a different question than what the specialist heard. And when we're working with products and processes, we want to improve quality, but that can mean many things, right? For your context, it might be the purity of a product, it might be how long it takes to produce it, it might be a particular function, and it might be how expensive it is to make it, or how much CO2 it requires to produce one item of your product. And before we can improve, it's really important that we agree on which of these properties we need to improve, because no machine in this universe can measure quality, because quality is just an abstract idea. Right? We need to be specific about what physical measurable properties it is we want to improve. And I should really stress that improve yield or improve price, or we want to understand how something depends on temperature. They're not clear goals. What you need to have a clear goal statement is something like, setting up a SMART goal, if you know that framework as an example. So one example could be that we want to increase the yield of our process in step 3, which is right now at about 70%, and we want it to get to at least 85%, and we want to be done before the end of Q3 of this year. So, and when we say yield, we mean yield measured by this specific protocol, and the total cost per kilo product must remain constant. I mean, it's free to become lower, but it must at least remain constant. And production capacity must also not decrease. Another example could be that we want to figure out which of 5 glues is at least 20% stronger than the one we presently use to join this material to this material in our production. We would like it to improve, but we're not going to swap unless we find one that is at least 20% better. And the strength of this glue we're going to measure in a particular way, and we are going to measure it by joining together flat test samples of A and B, even though in our production A and B are not flat, right? But this is what allows us to test it with this particular machine. And we have a full-time technician to run the tests and produce the samples for the next month, and that really, sets the sort of the stage for how much work and how many experiments can we actually do. And that will require us to make choices. And the good thing about Bayesian optimization in this context is that it really encourages you and your colleagues to have the really important discussion of what the goal is before you do anything. And because you can't use Brownie Bee without putting a number to quality, because we will not accept putting strength or yield in as a quality metric. We want you to state on a scale of 0 to 5 stars how far you are from your goal. So let's say that at your ideal best case outcome is 5 stars, and that is what Brownie Bee will target, and it will choose our experiments to move you towards that target. Because let's say you just have one thing you vary, and you have enough data that Brownie Bee shows you this graph for how your quality along the y-axis depends on this process factor. Now, if a quality of about 4 is not good enough for what you need, then you should stop at this point, because this factor, this single handle, will not get you to your goal of 5 stars, right? So we need to find something else in our production we can include in our experiments and in the handles to pull. But if it is good enough in the metric that you're working with, you should stop at this point again and use the solution and put it into production so that you can reap the benefits of this solution that you've found. All right. The second pitfall is about quality metrics, and any data-based approach suffers from the CISO principle, which is shit in, shit out, right? I'll illustrate this with the old board game Battleships. Battleships has really bad data because if your opponent just has a single ship on the other side that spans 2 squares, even though we have actually gathered a lot of data here, the data just said not good enough. And it's not very informative in where should we go to make the next experiment. If we change the rules of Battleships so that for each time you did an experiment, you got information about roughly how close were you to hitting the ship, which I've shown here as numbers. We can draw this in as the circles with the given radius, and then all of a sudden it actually becomes pretty easy to make a suggestion about where to make the next experiment. So these, even though there were only 3 data points, they contained a lot more useful information because they encoded how far were we from our solution in each case, right? And then you can dive into sort of the math details of sort of how much more information you get from measurements of quality on a quantitative scale versus just judging whether it passed or failed a quality. But on the whole, it's so much more efficient that if you judge quality today, pass, fail, it's nearly always worth it to invest in developing a quantitative number-based measurement. And reducing the noise will really speed up the process of finding the optimum. So how can you build that for Brownie Bee? Just to give you some examples to get you started, right? So sometimes we have simple quality metrics. It could be the yield. If we put in 10 kilos of raw material, we want 10 kilos out. So how many percentage of our input do we get out? And in that case, 100% would constitute 5 stars, 0% would constitute 0 stars, and we can just draw a straight line as a quality metric. And have a fairly simple equation for how to, calculate this number. Let me give you another example from the e-carpets company, which in their case, their quality metric was had to do with the top and bottom side of a carpet, how strongly they were glued together. And for them, it was important to hit a certain strength of this gluing interface, because if the strength is too low, you can just peel apart the carpet, which you don't want. But if the strength is too high, the carpet becomes too stiff to handle and to roll. So they had a particular strength of this glue adhesion that they wanted to target. And they knew roughly what strength would be too stiff and what strength would give too low adhesion. And in that case, you can set up a quality metric where if you are on the outside of the extremes, you can put in a quality of 0. And then in this, as we approach the desired quality, we want the score to approach 5. But we don't really want to punish small deviations from 5 very much. It's mainly when we get to sort of the edges that we really want the score to drop. And in that case, we could set up the quality as 5 minus the deviation squared away from our target here. So that will produce this shape. That's just another way of doing it. And on the whole, there are many ways you could build a 0 to 5 quality scale. Our experience is that it's not so important for the performance of the algorithm. The main benefit is just that you need to sort of think about the quality and put it into a number. That reaps huge benefits on its own. All right. Last pitfall I'm going to talk about today is choosing factors with domain knowledge. And here I want to share my favorite quote from the world of designing experiments, and that's from Doug Montgomery, who's a big figure in this field. And he once said that you should never let one person design and conduct an experiment alone, particularly if that person is a subject matter expert in the field of study. And that sounds slightly counterintuitive, but let me show you why that might be a good advice. Because domain knowledge is both a blessing and a curse when we're looking for new solutions. So let's say we have a process again that we think might vary as a function of temperature and time because of our background knowledge. We've just started in this new company. And today we produce, at this present setting. And we have a colleague who's been in the company for 20 years, and they say that, it's not going to help to increase or do anything to temperature or time. We have tried that many times. It doesn't improve quality. And they might actually be right about that, because the way that they have investigated these things is one factor at a time. So let's look at, if we change the temperature, we actually see that the quality drops slightly. And if we change the time, again, keeping everything else constant, the quality also doesn't increase. But in many systems, you might need to change both. And the real quality map might actually look like this. And we would need to change both temperature and time to improve quality. And just to show you, an example of that, a very concrete example of where this would be true. So if we return to the brownie, imagine that our present setting corresponds to turning on the oven to just 50 degrees and putting the prepared brownie into the oven for 1 minute. What's going to happen if we change time on its own, keeping temperature at 50? It's not going to help to increase time from 1 to 20 minutes. That's not going to bake the cake. Or if we stick to 1 minute and turn up the temperature to 200 degrees and put in the cake for 1 minute, it's also not going to bake the cake. What we need to do is to increase the temperature to 200 and the time to maybe 20 minutes in order to get a baked cake. But you will never discover that with one factor at a time, right? So what I've shown you today is that with a data-driven method, you won't waste as much time because you won't learn the wrong things, and you'll have a clear framework for how to actually conduct data-driven development. We've developed Brownie Bee in collaboration with a lot of companies which have given feedback in their use of it, which is why it looks as simple as it does. And it makes life easier in these companies now. And maybe soon it'll make life easier in yours too. Our goal with Brownie Bee is to make it easy to find optimal settings for a process based on a set of predetermined quality requirements. And with that, I would like to thank you for your attention and open up the floor for questions in the Q&A. You can begin typing those now. You can try Brownie Bee for free at browniebee.io. If you have any questions about the product or run into anything you struggle with, or you find a bug or something, please get in contact and we'll be happy to talk to you. I should also say that the math underneath is open source and still actively being developed in collaboration with Novo Nordisk. You can have a look at that on GitHub if you are of that persuasion. But other than that, I would say thank you for now, and let's turn to the questions.